So we're going to need to continue chapter 16 talking about spontaneity by looking at Gibbs free energy. Gibbs free energy is going to be the maximum amount of work you can get from a spontaneous reaction. So maximum amount of work. So let's see where this comes from. So we left off on the second law of thermodynamics. And what we said was that the change in entropy of the universe is going to be equal the change in entropy of the system plus the change in entropy of the surroundings. The system and the surroundings inherently are going to equal pretty much everything, hence the universe. We're going to get delta S of the system from our tables or from our charts. And we are told here that for a spontaneous process, this value right here, this change in entropy of the universe, has to be positive. If the change in entropy of the universe is positive for some reaction, the reaction is spontaneous as written. If the change in entropy for the universe is negative for a reaction, then it is non-spontaneous. And if the change in entropy for the universe is zero, then the system is at equilibrium. So we know how to get delta S of the system. Delta S of the system says that we look the values of the molar entropies up off the charts and we take the sum times the number of moles of the products minus the reactants. But we need to find delta S of the surroundings. Now, the surroundings, if we can understand those, we can figure out where this goes. So let us consider an exothermic process. So if we have an exothermic process, then this is our system here. This is our reaction. And if our reaction here is exothermic, then it is dumping heat into the surroundings. So if that happens, and we have heat flowing from our reaction, our system, into the surroundings, we know that as the temperature of something goes up, the entropy goes up, which tells us as the heat goes into the surroundings, the entropy of the surroundings is going to go up. And the entropy of the surroundings is going to depend on the amount of heat from the reaction. Equally, if we have an endothermic reaction, so if this reaction is endothermic, that means heat is going to flow from the surroundings into our system. This tells us that the temperature of the surroundings is going to go down. And when the temperature goes down, the entropy goes down. And so if we have an endothermic reaction, the amount of heat that is needed for this reaction to occur is going to affect the change in the entropy of the surroundings. So what can we do with that? So just make sure we think about this for a moment. If we've got a nice hot cup of coffee and our coffee is cooling, the heat from the coffee, and this is the only reaction that's happening, is our coffee is cooling. So as the coffee cools, heat is going to flow into the surroundings, which says that the entropy of the surroundings is going to go up. So the change in entropy of the surroundings is going to depend on the delta H, the system. And we're going to say that delta S of the surroundings is going to be or depend on the delta H of the system. And let's make sure we understand the signs. If delta H of the system is negative, that means it is exo, which means that the delta S of the surroundings is going to go up. So if this is negative, this value is positive. So we have to put a negative sign in there. And we find that as the temperature increases, this has less effect on the surroundings. And our equation here is delta S of the surroundings is equal to minus delta H of the system over T. Well, how does this help? Well, this helps because we can get delta H of the system, the charts, which means as long as we know the temperature that this reaction is occurring at, we can take and use that to find ourselves the change in entropy for the universe. So here's what we have. We have delta S of the universe is equal to delta S of the system minus delta H of the system over T, because delta S of the surroundings is equal to minus delta H of the system over T. And we know that once we have here system, we can actually use our charts. So we can use the charts that we have in our appendix to get delta S and delta H. Now, we know that if we have a positive delta S of the universe, our reaction is spontaneous. Now, the physicists don't really have much use for this, so they play with this equation. And what they do with this equation is they take this equation and they multiply through by minus T. So we know that delta S of the universe is equal to delta S of the system plus delta delta S of the surroundings. We know that delta S of the surroundings is equal to minus delta H of the system over T, because the change in the disorder of the surroundings depends on how much heat we dump into it. So if we have here that this is equal to delta S, and please note that these are both system, so we remove the choice of word system, and we just say that delta S of the universe is equal to delta S minus delta H over T, where both delta S and delta H come from the charts. And we take this equation, we multiply through by minus T. First of all, if we multiply through by minus T, we're changing our sign over here, and we're going to get minus T delta S of the universe. We're going to change the order of the delta H and the delta S. When we multiply through, we're going to get delta H minus T delta S. We're going to take this term right here and call this delta G. And our equation here is delta G is equal to delta H minus T delta S. Delta G is Gibbs free energy. Gibbs free energy is the maximum amount of work that you can get out of a reaction after you have changed both the entropy of the surroundings and the system. So it's what's left over to do work, and we get our values of delta H and delta S off of the charts. Now, the sign. So we have opposite signs from delta S of the universe. So our new second law tells us that if delta G for the reaction is negative, the reaction is spontaneous. If the delta G is positive, it is not spontaneous. And if it's zero, it is at equilibrium. So what are we looking for? Well, most of the time we are looking for a negative delta G for the reaction because we want a reaction to be spontaneous. So we need to consider the conditions under which delta G are going to be negative. So what we want out of this mess is we want our delta G here to have a negative value. So if we think about this, we can look at the signs. One obvious way is if we have a delta H that is negative, that's going to give us a negative equals a negative. That's going to help. And if we want to continue this, notice we're changing the sign here, but we want this entire mess to be negative as well. And the only way for this entire mess, this minus T delta S to be negative, is for delta S to be positive. So the first set that we're going to do here is that if we have a delta H that is negative, which by the way is exo, and a delta S that is positive, which inherently means positive, for a delta S means our system or our reaction is becoming disordered. So if we have a disordered reaction that's producing a lot of heat, the reaction is spontaneous at all temperatures. Now, if we have a reverse, if the reaction is endo and our delta S is negative, which means it's going to be becoming ordered, then nothing is in our favor, and this reaction will be non-spontaneous. And we have two other possibilities. If we have both delta H and delta S positive, which means it's endo, and it's becoming disordered. Disordered is good. we look at our equation here is delta G is equal to delta H minus T delta S. If our delta S here is positive, and we're multiplying it by a temperature, as the temperature goes up here, this reaction is going to become more spontaneous. If they are both negative, it is reversed, and it's going to be spontaneous at low temperatures. So another way of looking at it, if the entropy is going up and it is producing heat, it is going to be always spontaneous. If the entropy is going up, but it requires heat, it is going to be spontaneous at high temperature. If the entropy is going down, if it is becoming disordered, and it removes heat from the surroundings, then there's going to be nothing in our favor because the entropy of everything is going to go down and will never be spontaneous. And here, if it is a negative delta S and a negative delta H, it's going to be spontaneous at low temperatures. So we can play with our free energy. So we have delta G is equal to delta H minus T delta S. And so if we have a delta H and a delta S, and we know a temperature, we can calculate a delta G. Equally, we can actually use this to predict temperatures like boiling points and melting points, and we can use this to calculate T's. So let's consider this. So if we have a reaction such as nitrogen plus 3 hydrogens goes into 2 ammonias, we look at this reaction and we see that we're going from 4 moles of gas into 2 moles of gas, which means our delta S is negative. Now, can this reaction be spontaneous? Well, yes, it could be spontaneous if delta H was also negative. So the question then is, if delta H is negative, can we make this reaction occur? Well, we have to figure out what the delta H is going to be. Or we can figure out and actually calculate delta G. So there are a couple of ways of doing this. One, we can calculate delta G naught for a reaction. Delta G naught for a reaction, and we can do this at 25 degrees Celsius or 298 Kelvin. And we can do that because these values are also on the charts. And if we do that and we simply want the change in the Gibbs free energy for a reaction, the delta G naught for the reaction is going to be the sum times the number of moles of the delta G naughts of formation of products minus the sum times the number of moles of the delta G naughts of formation of the reactant. Now, like delta H, delta G naught of formation of an element is defined to be 0. It's a choice and it's a comparison point when we're looking at our Gibbs free energies. So what do we mean by delta G naught of formation? So let's just imagine that we are looking for the delta G naught of formation of carbon dioxide. Well, when we do formation, it means that we are making 1 mole of the compound of whatever it is from the element or the component elements. So if we were going to make carbon dioxide, it means that we're going to make carbon dioxide. It is going to be a gas because it's going to be the most stable stuff at 1 atm. Its component elements are carbon as a solid and oxygen as a gas. That's the stuff it's made up of. Inherently, it's going to make one of these. It requires it to be 1 mole of the compound, and that these terms, these elements, have a delta G naught of formation that is defined to be 0. This value we're going to find from the charts. And if we want the change in entropy for the reaction, we're going to do products minus reactants off of the chart. So if I wanted to know the delta G naught for the reaction here, and it would be a little zero here, at 298 Kelvin. Now the key here is 2 points. One, it's the delta G naught, that means the standard. 298 means we can get the value straight off the chart. So when we're given that value of temperature and we want standard, it means we go to our appendix and we get our values off the charts. Now, if you could change charts, your numbers may change a little bit. So what are those values? If we look them up, we find that delta G naught of formation of HgO as a solid is equal to minus 90.46 kilojoules per mole. And we have delta G naught for a formation of mercury is going to be defined to be 0. Delta G naught of formation of oxygen is going to be defined to be 0. And our reaction is going to be products minus reactants. So we are going to take delta G naught of formation. So we have 1 mole of Hg multiplied by 0 plus 1/2 mole of oxygen multiplied by 0 minus 1 mole of HgO multiplied by minus 90.46, and this is going to give us a positive 90.46, and this is going to be here units of kilojoules. Our delta G for this reaction is positive, so the reaction is not spontaneous. So again, if we calculate delta G and it's negative, the reaction is spontaneous. If delta G is positive, the reaction is not spontaneous, and we'll deal with delta G equal to 0 as we go along.